Alright, this is part 1 of chapter 11. This is the first of 2 chapters talking about our immune system. And chapter 11 looks at innate immunity. First off, an immune response is a physiological process coordinated by the immune system to eliminate antigens. So you've got a couple of terms or phrases in that sentence where it's basically your immune system goes through a process once it identifies a particle of some sort, in this case an antigen, that it deems as foreign. And the immune system then mounts an attack against it to get rid of it. Alright, the immune system has two key branches, so to speak, the innate and then the adaptive immunity. These systems are quite different. However, common features are that they both recognize a diverse number of pathogens, and then they're going to try to eliminate those identified invaders. And hopefully, both systems are able to discriminate between self and foreign antigens. Your self antigens are going to be any cellular protein, any cellular material that is yours, that is part of you as a human being. You don't want your immune system to attack you. If that happens, then there's a problem, and you have autoimmune diseases develop. Alright, and so the immune system is supposed to be able to distinguish self versus foreign. If you have a foreign antigen, then you should have that removed. Alright, table 11.1 compares innate and adaptive immunity. And some of the key features are going to be the response time. Organisms that have it, sort of, we're not really going to focus on that. Able to distinguish from self and foreign material. Can it kill invaders? Can it be effective against diverse threats? And then does it tailor response to specific antigens? And does it remember antigens? So if you get infected with X organism when you're age 2, or you get vaccinated against X organism at age 2, at age 6, at age 10, whatever the case may be, and then you come into contact with it at age 20, are you still protected? Alright, the innate immune system is basically material that you are born with. Alright, they are going to be immediate sources to fight off foreign material. Alright, so what are you born with? Well, you're born with skin. You should have been born with skin, alright? And your skin is part of that innate immunity to create a barrier between the outside world and your internal material. The adaptive immune response, though, this takes a long time to develop. Alright, long time here. It says 4 to 7 days. The number really is probably more, a better time frame of 10 to 14 days, really. At time 4, you can probably start seeing your immune system do something, the adaptive immune system, really start taking shape in that response against a particular organism. But generally, it's 7 to 14 days when that adaptive immune system, that adaptive immune response, works its wonders. All right, now, only vertebrates have an adaptive immune response, whereas eukaryotic cells have some kinds of innate immune responses. It's kind of interesting when you get down into that detail. But both should distinguish self from foreign. Both have mechanisms to kill invaders. And both are actually very effective against diverse organisms. Is it fungal? Is it bacterial? Is it protozoan? Is it viral? Is it X virus versus Z virus? Right? Very effective against many different types of organisms. And then can it tailor response to a specific antigen? So can the immune system respond specifically to E. coli or specifically to Streptococcus pneumoniae can it specifically respond against poliovirus. Right? The innate immune response cannot. It can respond against bacteria in general. It can respond against viruses in general, but it can't distinguish between polio versus hepatitis virus. But the adaptive immune response can. The adaptive immune response, which we'll look at in Chapter 12, has specificity. It is very specific to the specific material that is invading you. All right, and then can it remember? Innate immune system? No. Can the skin remember what it came into contact with yesterday? No. But it's just a barrier. It's just going to try to keep anything and everything out. The adaptive immune response, though, does have memory. And so it can respond to, at age 20, the virus or the toxin, the bacteria that you were vaccinated against at age 2 and 6. So that's actually a very cool component of the adaptive immune response. With the adaptive and innate immune response, there's actually 3 lines of defense that comprise both of those systems. Chapter 11 looks at the first line and the second line of defense. First line are barriers. All right, I've already mentioned the skin. That is a barrier. That's something you're born with, and first line there. But also part of the innate immune response is what's called the second line of defense. And that would be if an organism gets past the barriers. And so there are cellular and molecular defenses that can help fight off pathogens that get past those barriers. And then once again, the adaptive immune response, Chapter 12. All right, so 2 items on this slide here. Normal microbiota has a role in shaping immune responses and conferring protection. That's very important when you think about how many microorganisms you have on your body, in and on you. And the immune system is actually given some basically on-the-job training constantly with those normal flora, with the bacteria that are constantly on us. The immune system kind of samples it and is able to basically tell itself, yes, this is normal, and we're not going to attack it. And then once it sees something foreign, it's able to distinguish the foreign bacteria from the normal flora. And then also on this slide is what's called the hygiene hypothesis. The hygiene hypothesis, which, interesting, is an issue really in developed countries, and it's where there's actually really good hygiene. All right, so the hygiene hypothesis states that if you have a decrease in diversity and levels of microbes in your normal flora, that actually negatively affects your immune response. And the specific example is with worms, parasitic worms, helminth infections. In industrialized or developed countries, you don't have a lot of worm infections, not very many. If someone in the United States overall has a parasitic worm infection, there's a strong possibility that that person had traveled outside of the United States to a underdeveloped area of the world, or they have really, really bad hygiene and are, somehow digging into dirt and eating dirt. And because with helminth worm infections, those are generally fecal-oral contaminants, where the parasitic worm is utilizing the GI tract kind of as a hotel for a few weeks or a few months. But in developed countries, we see a lot of issues with chronic diseases, diabetes, asthma, allergies in general. And it's thought that because the helminths, the worms, are actually eukaryotic in nature, they have similar proteins to us, human beings, And if the immune response sees a helminth in our body, that's being the presence of the helminth is training the immune response to actually not attack the eukaryotic proteins. You take out the worms, and now the immune system is still trying to figure life out, and it actually then starts to attack us. And so the cleaner we are, the less normal flora that our immune system has that it can sample and have to participate in that on-the-job training. All right, so first line of defense here, it aims to prevent pathogen entry. Those defenses are categorized into three major groups: mechanical, chemical, and physical. Alright, with physical, you've got the skin, and that really is the major physical barrier. Mechanical, you have a process. Alright, and the two major processes that are seen on this figure are tears that lubricate the eye to allow for proper eye function, but also to rinse microbes away. We probably don't even recognize how many tears our eyes actually shed each day, but it's a lot, and it's to keep the mucous membrane of our eye, to keep the organisms moving past, not getting actual contact to the eye, because it's actually a pretty good portal of entry for pathogens. Right? Also, the respiratory tract with the cilia, what's called the ciliary escalator of the respiratory tract, along with the mucus. Right? The mucus traps invaders, makes it sticky, and then the cilia can beat in a, I'm blanking on the word, a systematic way to allow for the mucus along with the bacteria, as you see here, to get moved out of the respiratory tract and keep the microbes from moving further down into the respiratory tract. Right, also mechanical would be peristalsis, urinating, right, moving material out of the body as a mechanical process. And then chemical. Chemical are going to be those chemicals that are around all of the time. Right, there is a chemical called lysozyme. I think we've talked about lysozyme before. And lysozyme is going to target the cell wall, the peptidoglycan of bacterial cell walls. And you can see here that the blue is the lysozyme, and it's targeting the cell wall to actually allow for holes to be created in this bacteria. And then you have lysis, and that cell's going to die. But lysozyme is found in tears, in mucus, saliva, breast milk, maybe even sweat at very low numbers, low amounts. And that helps to control the amount of bacteria that are able to survive in that environment. And then there's the stomach acid. Right, the stomach acid, our food is actually quite dirty microbiologically speaking. And so the stomach acid can kill microbes, pathogens that get on our food and down into our stomach. Then there are what's called AMPs, antimicrobial peptides, and that's what this little guy is supposed to be. And there are a lot of different kinds of AMPs. Those AMPs are going to destroy pathogens. This is again showing a bacteria cell. And they do a really good job. And all of these are non-specific. They see something foreign and they're going to attack it. Alright, mechanical barriers wrench, flush, and trap pathogens to limit their spread. We mentioned most of those examples there. The physical barriers, the major one is skin, with the epidermis made up of tightly compacted dead epithelial cells, and when those cells slough off, they take away the bacteria along with it. And that is where we're going to stop part 1.